So when I was somewhat younger, after a short gig in algebra, and then I switched to analysis. At that time, people were studying nonlinear PDEs, and they tried to see what is essential in a PDE and turn it into some kind of a problem if you were studying nonlinear PDEs, into a problem in nonlinear function analysis. So to identify basic principles, and then once you turn it into a problem in nonlinear function analysis, you apply some tools which were provided by the theory. Now, shortly after I sort of started there, it turned out that what I observed is that people actually proved abstract results, and then they were desperately looking for applications, which of course tells you that is a moment where you should leave. And then at that time, an era started where people were looking at nonlinear PDEs. They used more ad hoc methods, but they also studied more complicated PDEs, in particular those where you had lack of compactness and so on. So before the era was something like you looked at PDEs, not say elliptic PDEs, nonlinear elliptic PDEs, where you had compactness, and then you were studying questions of multiplicity, how many solutions are there, and so on. And then, of course, there was this era of more complicated problems, but in fact, in many cases then when you solved them, you used some ad hoc methods which were sort of recruited from this old toolbox, and the papers got longer and longer and longer and longer and so on. And what I want to talk about is that there are actually conceptual ideas also for this kind of problems to describe them, which become particularly useful if you start very complicated systems of nonlinear PDEs, nonlinear elliptic PDEs, which are related to each other, like it occurs in symplectic field theory, Floer theory, and so on. Now, the reason that things are a little bit complicated is that in some sense, the language is missing. And one of the things one has to deal with is that differential geometry is too special. It has to be generalized. And in order to generalize it, you have to go a little bit back to calculus and study some of the problems there. So at the end, what will happen is that you can generalize differential geometry by just allowing more general local models, and you don't have anything to change in the theory. You can take over the whole building, just say instead of local models being open sets or something, just take something else. But what you need is a notion of smoothness and the chain rule, basically, and then you can take any recipe you want. And it turns out there is such a language to describe phenomena like bubbling off, stretching the neck, everything from the chamber of horror in analysis. And let me describe some of the ideas behind that. Okay, so I think it's good to, in order to develop such ideas, I mean, you need a good example to begin with. And a good example which has a lot of structure and you can still do something with this is symplectic field theory, which was introduced by Elias Berg-Gieventer and myself about 2000. Now, Tom already explained some of the background. So you have an odd dimensional manifold, you have a contact form, it defines a Reb vector field. You have the splitting of the tangent bundle into a line bundle generated by the Reb vector field and the kernel of the contact form. And then what you do is you fix an auxiliary structure, basically a complex multiplication on the contact structure, and then you can extend it to an R invariant. Then on R cross M, you can extend it to an, which is now even dimensional, to an almost complex structure, which is R invariant, which pairs the one in the tangent space of R with the Reb vector field. So now what you want to study is this PDE. Now the general scheme is of course the following. We know that already since Donaldson, which works quite nicely, that if you study some geometric problem, so usually you find a certain amount of auxiliary data like Riemann metrics. If you study symplectic manifolds, almost complex structure compatible with the symplectic form. And out of this, you cook up elliptic PDE, and then you count solutions. And if you have a good way of counting solutions, that might be an invariant of the geometric structure. And so if you try this, in this particular case, you look for pseudo-holomorphic curves from a punctured Riemann surface into R cross M. So you take a closed Riemann surface, you remove a finite number of points, and it satisfies a nonlinear Cauchy-Riemann equation. You might have some marked points on this, so let me maybe show you a picture. And this already shows you some of the properties of this equation. So if you study this nonlinear Cauchy-Riemann equation and remember that the Reb vector field was coupled with the R direction, then periodic orbits cross R are actually pseudo-holomorphic curves in this picture. That is also related to the Weinstein conjecture here, by the way. If some of the invariants are non-zero, it would prove the existence of periodic orbits. So now what you're actually interested in are not the tuple consisting out of the Riemann surface, complex structure, ordered marked points, punctures, and a map, but you're only interested in these things up to equivalence. So you say two tuples are equivalent, provided there is a biholomorphic map between the domains which is underlying, preserving the marked points, preserving the punctures, which relates the two maps which were defined there up to the following, namely observe on R cross M we have an action by R, so you're allowed to change the R component. So these are the objects you want to study. So if you draw a picture, what they do, an interesting feature is that near a puncture, solutions of this PDE want to approach a periodic orbit. Yeah? So these are periodic orbits over cylinders over periodic orbits, and if you look, for example, if the underlying domain is a punctured torus, then if you go on concentric circles to the puncture, you would go either to plus infinity and minus infinity, trying to approach such a cylinder. Then, of course, knowing that there's Floer theory and so on, you would think there should be a Floer theoretic picture in the background. And in some sense, what we want to study are these things, but it turns out there are some compactness issues, and we have to study some more complicated things. Namely, you can imagine that if you study such an object lying in a family, a source of non-compactness is that certain parts go to plus infinity and to minus infinity. Now, everything is R invariant, so what that would mean is that you get that the relative position of certain non-trivial parts of the holomorphic curve goes to infinity. And then you have to study this kind of objects, which you have to add to a compactification. So you have layers of arrangements of pseudo-holomorphic curves, say the top layer, which is certain solutions of the equation for where the map goes into Rm. This is one copy of R cross M. Then you have a next copy of R cross M where you have solutions in and so on. And the basic feature between this and this, how does that work here? And the basic feature is, so you have a top level, there are periodic orbits here, you have a bottom level, and those periodic orbits come from above, matching the one from below. So now, so this is some of the elements in the compactification, and with Bourgeois, Eliashberg, Giventhal, Wysotsky, and Sehner, we proved that that is indeed a good compactification. Now, then all these things which you see here, they satisfy elliptic PDEs, yeah, a nonlinear Cauchy-Riemann equation. And now you want to count things here in some way which is independent of certain auxiliary data which you take. Now, besides this compactness issue which I already addressed, there are numerous transversality issues. So you want to count things, and usually maybe they shouldn't be even there from a Fredholm index point of view. Sometimes there are too many, and so on. So it's a problem which is not in general position. You have a lot of structure, and in order to count, one of the things is you have to bring it in general position. However, you can't do that either. So you have to show that you can bring it in a best possible position so that you can count certain things. So that is the issue. So now, from a classical perspective, how would you describe this? So you have a solution of a nonlinear elliptic PDE. You might choose some kind of a setup of a Banach, a Banach bundle over an orbifold. You have a section of this. The zero would be the solution you're looking at. And then you would try to bring this in general position. Of course, since you're already in an orbifold setup, there are already some issues there. Now, the issue which I mentioned at the beginning, you have this lack of compactness. So something goes to infinity, so you get an end because some estimates blow up. And then sort of this ad hoc way is to explain the infinity by gluing something in, which is a solution, a modularized space of a solution of another PDE. But that also might have some compactness issues, so you have to glue some other stuff in. So if you describe that in a way where you have to deal with, say, infinitely many interacting things, actually it gets pretty messy in general just to set it up. And as it turns out, if you generalize differential geometry, things like bubbling off and so on, breaking the neck are actually smooth things. And at the end of the day, you end up with a Fredholm theory as you know, the classical Fredholm. I will say a little bit about that later on. So now, if you study a nonlinear elliptic PDE, of course, you look what are the basic features of this, of a solution, and then you build a space of functions which are not necessarily solutions of this, which incorporate these special features. And one of the important features is that solutions, in the case that the contact structure is non-degenerate in some specific way, approach the cylinders in an exponential fashion. So rather than looking at solutions, then you can look at a space of functions which has this kind of objects. They are in some Sobolev class here, so they look a little bit more wiggly, so they are not solutions. You have the notion of equivalence. And let's note something here which I use later on. Again, that if you look at such a configuration here, that would be a level 2 curve, then you can associate to this some topological data, which would be the outgoing periodic orbits, the ingoing periodic orbits. You could look at some relative homology class or relative homotopy class in the space of equivalence classes of such objects. And let's call this, you can associate the arithmetic genus, so let's call this a type. So let me just write such a green box here. These are the outgoing things, the ingoing things, and that thing has a type. And you observe that if you have, so this is now a box. Suppose you have another box here where the ingoing orbits match up with the outgoing orbits here. You could sort of concatenate the two boxes, and associated to this is obviously a new type. Yeah? So you could think of type A, type B. If you remember that A and B incorporate some topological data, there would be an associated natural type again. That will actually be important for doing algebra. So let's. So there's some basic feature in this problem, which, whatever I say, is not precise at this point because really the mathematics is missing to make that rigorous. I mean, I will tell you how to do that later on. So if you have these different types, you can create a new type. That's obviously from the description. Record this as type, the left source, right source. If you have something of type A and B, you can construct something of type C. That is some of the features which ultimately make the algebra. So you have a set of all types, and you have sort of relators between them. And the overall structure of the problems is something like this, but it's not useful at this point if you don't know what Z actually is. You look at all equivalence classes of such objects, then this thing should have a boundary, and the boundary can be written as a fibered sum, which basically means that the face, this thing should be something like a smooth object, ideally with boundary with corners, where the faces can be explained by other problems. That's the kind of structure which you have here. Then you have a bundle over this. In our case, we have a Cauchy-Riemann equation. The zeros are precisely the solution spaces for these configurations. And this Cauchy-Riemann operator is compatible with this fundamental equation. That's the structure. Now, of course, people use this structure, but in some sense by ad hoc methods. I will tell you that this thing, in general, because of bubbling off phenomenon and other phenomena, like, for example, you're studying technically nonlinear elliptic PDEs on varying domains where you can sort of necks can turn into nodes and this kind of things. So it turns out that if you study the space of function near such an object, there's no manifold description, there's no Banach manifold description for these objects. That is one of the problems. But it turns out there is a generalized differential geometry where this actually can be done. So here's a basic question. What kind of structure can you put on this set Z? Now, if you could put something like a smooth structure on this, and you would have the basic packet of Fredholm theory, like an abstract transversality theory, an abstract perturbation theory, things would become quite easy. If in addition you would have a nice toolbox actually to bring a concrete problem in such a form, would be even better. So now, this space, as I said, is naively would say it's perhaps a Banach orbifold, but because of all the analytical issues, it is not. And one of the problems is precisely if you look at a family of holomorphic curves and so two major parts drift apart, you get a long neck. And then this thing decomposes and you get two objects in two different manifolds. And if you want to describe that in a Banach space setup, this is a violent process, it's a change of the domain. You're studying elliptic problems where the domain changes. That's hard to describe with classical means. So here's a toy problem for this, where you can actually analyze. It's precisely the same degree of difficulty. So, but here I'm a little bit more concrete. So consider the following. So forget about this for the moment. You look at the following situation, where you look for maps. You look for maps defined on a finite interval, say of the length 0r, that is here, which say takes the value 1 here and the value -1 there. Now you make this interval longer and longer and longer, and in the limit you get two different half lines. So now there is, if you just say that this should be of Sobolev class H1, then and this should be in H1 as well, with, so that it decays in some way to 0, then on the disjoint union of all these things, you can put a second countable power compact topology, which on each of parameterized by the length of the interval, let's say the length here is infinity, which on each fiber gives sort of the standard topology, but so that the overall topology is connected. And these things here are actually open and dense in the whole space also containing these things. But then if you want to, for this natural topology, want to come up with a natural way of writing this, finding a neighborhood, which is in some sense an open set in a Banach space, which describes the neighborhood of this thing here, which contains object of these things, it's basically impossible. So how can we describe? And this is, of course, when you understand this, you understand the thing with cylindrical ends and other things as well. So the thing is, we want to have some kind of smooth objects on things, some kind of smooth structure on things which are not locally homomorphic to open sets, at least not in any useful way. So here, that's the question, the first question. Can we generalize differential geometry to describe this? Of course, mathematicians are sort of minimalistic, so you would like to take over this classical building of differential geometry, where we have at the bottom open sets, same Banach spaces, smooth maps between them, important the chain rule, and of course also it's important that they have partitions of unity. Then we have all these recipes, and the recipes don't really care too much about specific things here, they only care about some formal properties. So the question is, can I put something in here so that I can use whatever construction comes here out, I can use it to make similar constructions, but with some more general local models here. So this is a joint work with Wysotsky and Zehnder. So now it turns out we have to go back to Leibniz and Newton and think about a little bit about smoothness in higher in infinite dimensions. But before I do this, let me recall what, so everybody knows what differentiability in finite dimensions is. So people who are not generally going to infinite dimensions might have certain romantic ideas about differentiability there. So let me give you the straightforward generalization, which is called Fredholm differentiability, which everybody who does nonlinear analysis does. So this is a generalization. So if you started with this picture here, if you say with open sets in finite dimensional spaces, and then you just take a straightforward generalization to Banach spaces, then you see there's no problem except that you have to assure partitions of unity which are not generally available in Banach spaces. So the differentiability, the standard one is the following. You require that there is a linear operator and you have this kind of approximation property. Then it's differentiable at the point x. Then if this depends continuously on x, it's continuously differentiable. So then you get a map x goes to d of x in the operators, and you say if this is differentiable again in this way, then the original map was C2 and so on. So now, of course you won't understand this bad news exercise, or only a few of you at this moment, but let me say the following. So when people did fixed point theory, which is of course a classical subject in algebraic topology, at some point they were thinking of how general can you actually do fixed point theory. So they started, say, for maps from an open set in Rn into Rn and associate a fixed point index to this. And they found out that you actually can extend it to Euclidean neighborhood retracts, and then if you go to infinite dimension, have some compactness to absolute neighborhood retracts. So now here's the word retract. And I show you if there would be smooth retractions, for some notion of smoothness, you can immediately generalize differential geometry. However, the bad news exercise is the following. If you have a map R from U to U, which satisfies a property, R is a possibly nonlinear map, that R composed with R is R. Let's call this a retraction. Let's assume it's smooth. Then by simple implicit functions theorem, which is valid in this context, you can show that the image of an open set is a submanifold of U. However, it turns out if you generalize the notion of smoothness, there are interesting sets which are not submanifolds, which even can be infinite dimensional, finite dimensional, mixed dimensional, which nevertheless are smooth in the following way. So here is good news. Of course, I have to then be more precise about this, but here are the formal things. So there are other notions of smoothness for which smooth retractions can have images with varying dimensions. Now, if you see, what I mean notion of smoothness is you can say what a smooth map is, and you have the chain rule. So you can speak about the tangent map, and assume we have a notion of smoothness, and we can associate to the tangent map. And of course, if you apply T to composition, you get this out. So if you apply this to R, you see that the tangent of a retraction is a retraction itself, because TR composed with TR is TR. So now if you take the image of a set under retraction, you can define the tangent of this as the image of the tangent of U under the tangent of the retraction. Yeah? And it turns out that you can, by formal properties, show that this definition does not depend at all on the choice of the retraction as long as it's smooth. It's a property of the set itself. So now, what should be a smooth map between such objects, images of retractions? Well, you just say that the composition with a retraction should be smooth. That actually also doesn't depend on the choice of retractions. And the tangent of a local model now, so this retraction will be now our local models, is this. And of course, now we can generalize the differential geometry by allowing these new things as our local models. So now it turns out that the space Z in SFT is an orbifold in this theory. So it's locally like a smooth retract divided by a finite group. But it's not locally, it's not a Banach orbifold, but it's locally or something of that type. So now, let me give you you even get new things in finite dimensions. So this guy here actually has a smooth structure and a tangent space. So let me explain that guy. So here we have an open disk, and we delete 3 disks. So then we attach these antennas here by adding point here, some hands a body and so on. And what you can do is, there is an embedding into L2 of R so that the image is a smooth retraction of a neighborhood. So now, such a guy also would have a classical description, because you could say the following. You take the open disk and then you stick in these antennas here, but of course then you have to say that certain sticking in of antennas are equivalent, because you have to sort of get the infinity germ here, but you see how clumsy that is. You get a thing, and then you have an equivalence class of sticking in things, which then gives you an embedding of the tangent space if you come from the outside with the tangent space of this one. The advantage of this language is this object can be defined as follows. It's a second countable paracompact space which has an atlas where the transition maps are smooth, precisely as before. And this is what makes the language so efficient in this context as well, because the general descriptions here are by sticking in something from the infinity and so on. If you do it correctly, it's the same language as before, except the letters have a more general meaning. Okay, so now how can we define this kind of retractions? And what is the underlying notion of smoothness? So as you see here, it's definitely inspired by elliptic theory, and the thing is, we have to find a class which is flexible enough, of maps which is flexible enough, and which in fact for our applications has to be able to see corners. Boundary with corners should be a notion which exists in that category. So now what you do is you have to put an additional structure on a Banach space, namely if you have a Banach space you define SC structure. SC comes from scales, and scales have been of course studied in interpolation theory for centuries, I guess, or at least maybe, but for a long time. So an SC structure is just a nested sequence of Banach spaces with compact embeddings that you require that the intersection of all of this is dense in every EI. Now it turns, so here's a requirement of this compact embedding business, and it turns out there is actually a generalization of this here, which contains the classical generalization of differential geometry differential geometry to infinite dimensions as well. Namely, there's a theory where you don't need to have this compact embeddings here, and in this theory, if you have the constant sequence E, that would be the classical theory. Yeah, so you play around with the scales. So the classical theory is a theory associated to E. However, you don't have the compact embeddings, and it turns out this is not very useful for the applications in mind. And it turns out that the requirement of compact embeddings is actually very important, and this generalization to infinite dimensions is completely disjoint from the other one unless you're in finite dimensions. So now here's an example. Of course, you take the L2 space and you take the Sobolev scale on an interval, for example. So now what is a tangent space here? Now in this theory, in general, you don't have a tangent at every point. You only have it at good points. And in this example, which I gave you before, this finite dimension example, in fact, you can have an embedding where you have a tangent space everywhere. But in general, in particular in infinite dimensions, you give up that you have tangents everywhere. And if you think about what you want to do, ultimately, you want to apply to elliptic PDEs where you have regularity and so on, and the solution set usually is a sufficiently smooth object and will actually, on that level, you will have tangent spaces. So now, let me observe the following formal structure here. If I have a Banach space with such an SC structure, then of course on an open subset I get such a structure. And then if I start with any I here, I have an induced structure by just taking the tail end of that structure starting there, and I denote this by U upper I. So now the definition of a tangent is just U1 plus E. So in this example, the tangent of L2 would be H1, Sobolev space H1 plus L2. So the theory is you just randomly say on which level what kind of tangent vectors you're allowed to consider. It doesn't really matter. It just should be in a nested sequence of things. So it's clear what the notion of being continuous is. Of course, it should preserve this filtration, and the map induced from UM into VM should be continuous. That's clear. So now more interesting is the notion of differentiability. Of course, it looks almost like the classical notion, except that there are different, you approximate for different topologies. So a map is SC1, that's the equivalent of being C1, so it should be SC0. And for every point x of regularity 1, view this index as a regularity, there should be a bounded linear operator from the 0 level to the 0 level so that you can approximate in this way. So observe here, the variation is taken on the 1 level. Then you view everything in the 0 level, and you require, now you can define this tangent thing here because x, in order to define this, x has to be on level 1. So you actually, at a point, in order that this makes sense, you're at such a point here, and you require that this is SC0. So then what is important is that you have this compactness, and you can show the chain rule holds, and there is a version of differentiability where you restrict to relatively open sets in partial quadrants and so on, so that you can also show that such maps actually see corners. So you cannot straighten out a vertical for such a map.
Divide by the normalization.
Yes, I want. Yes, right. So I divide here.
But the one normalization one.
Yes, okay, so. I mean, sometimes I try to write on the screen, but people didn't like that. Yes, okay. So I divide here. Thank you, Dusa. I divide there. Yes, thank you very much. Okay, so now, having this, we just build our differential geometry. So we fix, we look at what I already discussed at the beginning. We look for smooth retractions. And then, so these are the smooth retractions. Then we can say what I already said that before, what a smooth map there is, namely, you take any smooth retraction onto the set O, and the composition should be smooth in this way, just defined. That's the tangent. So, and this turns out, this notion, it doesn't really matter what you take here. As long as it's compact embeddings, you get new notions of compactness with non-trivial retractions, where the retractions actually in general have varying dimensions and need not to be submanifolds. Okay. So in this theory, you have a lot of flexibility. For example, you can go smoothly from infinite dimensions to dimension 1 or 0. So for example, on L2 of R, there is such a structure, so that there is an SC smooth map from here, where every RT is in fact a linear projection. You start with the identity here, and you go to 0. So you go from the fibers here are L2 spaces, and you go smoothly to 0. So that, of course, has some advantage. For example, if you starting an elliptic PDE here, where you work in some Sobolev setup, you can actually homotop it to smoothly to combinatorics. If you find the right way of combinatorics to homotop it to. So now, let me remind you, so now we have this more generalized language where we can talk about more general smooth spaces. So we can take any construction we want from differential geometry. Of course, it's usually good to check, because there's sometimes like certain things like in finite dimensions you say proper, but you have to think what actually does it mean in infinite dimensions and so on. So one should always be careful. But basically, every construction from differential geometry has a good shot in that theory to be generalized. So now, of course, there's always a price to be paid. Now, in the classical theory, we have the strong notion of differentiability, and if you have a map, remember now a Fredholm operator, a linear Fredholm operator is a linear operator which has a finite dimensional kernel and a finite dimensional co-kernel, and a nonlinear operator is one whose linearization has this property. So let's assume now we have a Fredholm operator which has a nonlinear Fredholm operator which has a surjective linearization at a point. Then of course, with respect to the classical notion, we have an implicit function theorem, and we get a structural theorem about how the solution set looks like. Of course, the price which you paid at that point is the following. So you start, say, with an elliptic PDE, you build this Banach space setup when you can, then you have the strong form of the implicit function theorem, then you find the solution spaces, and then you throw everything away, because you're interested in the solution spaces most of the time. But the solution spaces will be nice submanifold of a big space with a lot of structure. So now what I'm doing here is we streamline the whole thing. We say, maybe let's work and do a theory in a space of garbage. Except that garbage has a little bit of structure that on a solution set, it would be enough to say you get a smooth structure. Yeah? Now, what should be a Fredholm operator? Obviously, and that is of course the objection, now the analysis went down. Of course, to some extent it did, but there are still non-trivial classes of maps for which you have an implicit function theorem. So now the price to be paid is now that something is a Fredholm operator, provided it has near points, near a certain number, near a certain class of points, nice normal forms. But normal forms here means they can be written like an isomorph. After a change of coordinates in your new charts, now remember, we have many, many more coordinates than before, yeah, because we have this flabby notion of coordinate. And what you want is that something is Fredholm, provided it looks sufficiently nice in local coordinates near point, just a germ. Now it turns out that is in general not so difficult to verify. It's on the same level like showing that some inverse is bounded like in Taub's gluing and so on. Something you can't avoid. I mean, in all these applications there's some work. But there's not more than that, because it turns out that this kind of definition, which I'm not going to write down precisely, I'll say a little bit more about it, is a definition about germs. And it turns out there's a general theorem that says if you have these nice germs, it actually fits smoothly together, an abstract theorem. Okay, so now, then there's of course one issue I also have to address. Remember, for these retractions, you have spaces with varying dimensions, so the domain changes. And if you want to have a Fredholm theory and the solution spaces should, for example, be manifolds, then it's better that if the fiber also changes in some particular way. Now it turns out in applications, they always jump in the same way. And that, because of that, there's actually quite an easy notion. So, but let's start with a little bit fundamentals first. So what I need for the following is the following. So we want that solutions are still, even the surrounding spaces are pretty bad, we still want solutions to be manifolds, orbifolds. If it's really bad, branched manifolds or branched orbifolds. So with this more general notion of a local model, we can define bundles, and of course, the bundles are defined also by retractions of such objects where the only requirement is that they are linear in the fiber. Yeah? So you study retractions. So the local model here is the set which is an image of a retraction, and then for the bundle you have something of this kind where in the fiber you retract linearly. So that means this is a projection. But here of course, this projection in general, of course, do not depend at all continuously as operators on the parameter. Yeah, of course, otherwise the image of retractions would actually be submanifolds. And a section then is, of course, a map from here. So the principal part would be a map from one of these retracts to some Banach space which satisfies some condition of that kind. So here, and I'll show you a picture, so maybe the picture is actually more illuminating for this. That is what's written on that transparency in a picture. So what happens usually is the following. So I said these spaces can have varying dimensions. So you come here on a one-dimensional thing, it suddenly becomes two-dimensional. Now suppose here you have this bundle over this. So the fiber over this point would be zero-dimensional, and suppose here over this point would be one-dimensional. So then, if you would have a section of this, then you see the relative dimension would be 1. You would expect, ideally, a one-dimensional solution space. So now the structure of all this problems in application is that there is a natural stabilization before. Usually, say, in Gromov-Witten or in Fleur's, in Gromov-Witten, it's a Cauchy-Riemann operator acting on spheres with two prescribed points where it takes opposite values, a linear operator where you can stabilize this. So you add artificially a few dimensions to it, here 1. You add to the top 1 dimensions, then you can add an additional isomorphism to this, and this extends in a smooth way in this context over this place. Yeah? So the general picture is when bubbling off occurs, you go from an infinite dimensional space but of lower dimensions when the bubble occurs to a high dimensional space in the surrounding space. Of course, the moduli space goes down if it's in general position. But so when bubbling off occurs, before it occurs, there's a procedure that you add linear isomorphisms to this by adding something to the fiber, and this family goes smoothly through. It's not entirely canonical, but it always exists. And in examples, these are always like the Floer operator at a periodic orbit is linear isomorphism, certain linear operators, linear Cauchy-Riemann operators, and so on. So once you see a few examples, you see them all over the place. Let's call this a filling. So there are some conditions. So basically what you do is you extend, so you have a problem defined on a retract, which goes in a bundle over this retract, and you extend that problem to open sets, so that if you retract, it's the old problem, and it doesn't add any additional solutions to it, and gives a bijection between the stuff you added downstairs to the fibers you added upstairs. So let's call this a filled version of our original problem. So I didn't change the solution set. It's something like this. Let me also illustrate at this point that if this here, you see, this object also is a smooth retract, so you have this open 3-ball, you attach a Saturn ring where there's no point here, you attach this handle, and you could think of a bundle where the relative dimension jump is the same, and then if you can of course talk about transversality because we can talk about smoothness, and that would be a solution set of the problem. Okay, so you start with this. So I have to say what Fredholm is. So Fredholm is you start with the sections, then you find a good filling. In applications, this is always straightforward, and then you show that this filled version has some kind of, belongs to up to change of coordinates to a nice class of things. And the nice class of things which is identified, but there are actually more general classes than this, but they're more complicated to write down. So the theory hasn't been pushed to the end yet. Yeah, you can go much further than that. So here, but this class is sufficient for symplectic, for all these Floer theories, at least the symplectic Floer theories. So you look at f minus f of 0. Yeah, so you may assume that you study near the point 0. If for the filled version, you take the difference. And then this map is something like a finite dimensional map, which is this. And the other part looks like the identity minus a contraction. So if you look about Taub's gluing and so on, so if you assume it's surjective, you can always bring these things into this form. So this is only a condition on germs, and you see here, this should be a contraction for some epsilon provided on some level m, the things are sufficiently close, where this actually depends on the level. So you can be, if you view the index as higher regularity, if you go to higher regularity, you have to be closer and closer. So you get all these germs, but it turns out there's an abstract theorem that if you have this, there's a global implicit function theorem for this kind of maps. Of course, there's a certain amount of nonlinear analysis work, because in order to understand this SC smoothness, so we had to sort of reduce some of the nonlinear analysis to find a sufficiently large library for SC smooth maps, which of course you can sort of reduce to classical studies. But then also, you can, how do you make estimates for an elliptic PDE when the domain changes? So we had certain thoughts about this, how you can view this from a conceptual point of view, which I'm not addressing here. So let me now summarize what we have at this point. So we have now more general local smooth models for spaces. That means we have many, many more charts. we have many, many more coordinate changes. And now you can imagine if the definition of a Fredholm section is it looks good in local coordinates after some procedure, that many, many things are actually now Fredholm which weren't before. And that's in fact true, because as I said, you can go from infinite dimensions to finite dimensions in a smooth way with this operator. And this gives enormous flexibility, so you can do a really lot of wild stuff, and it applies to this theories here. So now let me tell you a little bit how that is useful. So I'm coming now to the beginning of this lecture where I pointed out. So now you can actually do a lot of nice algebraic things which you couldn't do before because the description was a little bit complicated. But so we study. So here's now the general picture. So you have infinitely many Fredholm problems, say countable set of Fredholm problems, and these Fredholm problems are defined on this new smooth spaces with boundary, and if you have a point on the boundary, you can explain it by using the other Fredholm problems. So think of this like follows. So there's a wall, so I'm looking in one component, and I have a Fredholm problem of index 1. So I lie in a one-dimensional family. So I'm going through this space, and suddenly I hit the boundary. Then I look in my library, and this can be written as a product of two solutions in another space. And then, if there are some relations between the indices, you get another point which moves on. And this is a structure in all these problems. And what I'm describing now is a theory, an algebraic theory, which is a much more low level of what we actually see with the Floer homologies. Because I think everybody there already goes too fast by being indoctrinated by Morse homology. In Morse homology, well, Morse homology told you what to do. Yeah? But what you do is, you do in fact a representation of another object. Namely, you use the fact that you have an input, one critical point, and the output. But it turns out there's a theory without all this, which you can do as well. If you apply this to Morse theory, and it's actually an invariant of the isotopic type of a Morse function, and then if you do another representation theory of this, you get Morse homology. So there's more structure there. And I think on this level, it might very well be feasible that some representation theory of the structure which you do for SFTs, this basic SFT picture, yeah, you look at all moduli spaces, that some representation theory actually gives embedded contact homology, and the other representation gives the usual SFT. So, but it would be difficult to say it if you don't have the language. But now you can say these things, and I will describe a little bit what the picture is. So we have a problem where we can explain the boundary of the space by the other problems, and the Fredholm operator df is in fact the restriction of f to the boundary is related to the other Fredholm problems. In general, like one boundary phase here is the image of a product here. Of two components. That would be a possible situation. So now, in general, there are a lot of issues which I will now highlight and which lead to actually interesting things. So let's first forget the Fredholm theory. Let's do some algebra. So we have this letter of all types. We have relators between these things. Say out of type A and type B, I can construct type C. And we have this thing. So here is this is a fundamental structure. You have the types, the relators. So think of this as pi 0 of z, for example. Think of such an object R consists of such things as a face, describing a face in the boundary of z. And you have a grading, and you couldn't have other gradings like the two gradings. But the grading you should think of is the Fredholm index plus 1. For those, if you do Morse theory and you divide out by the R action, that explains the 1 here. Then you divide out by the R action, you get index 0, that is what you count. So now we play the following game. So given this points, this triples R, and the alphabet which we have, we look at the generation sequence. We start with the letter C. We look if A, B, a left source and a right source gives C, and then we can replace C by AB. Then we look up again. If B comes there, it didn't, so A comes. We have X, Y goes to A, we can replace it by these letters there. So starting with any C, what I will require is that we only have finitely many degeneration sequences. And another thing, if I start with one letter, go to 3 letters, there are precisely 2 ways to go to there, namely first contracting on the front and the other first contracting on the back. Yeah? You see, if you have 3 letters, if you go from 1 to, you go backwards, start with 3 letters. In order to get there, I contract it at the front or on the left. If I go from here to here, I contract the last 2 letters. And what I require is, if I can go from here to here, there are precisely 2 ways to go. One is contracting on the front and contracting on the back. So these are just the requirements for this object. Yeah? So now, whatever happens to our Fredholm problem actually will be counted in terms of a construction associated to this, what I call a degeneration structure here. So here's what I explained before. So you start, for example, if you have a homotopy, so the homotopy parameter is, of course, you want that the homotopy is compatible with your structure. Of course, that might be a lot of structure which is conflicting with transversality issues, yeah, in general. So then you start happily here, and then suddenly a solution branch stops, but you know it has to, if you have compactness, it has to hit the boundary, so you can explain this as a product and so on. And by this grading, there are certain relationships between the Fredholm indices and so on. So now, how would we count things? We would count, so here, of course, I want to count solutions on a manifold with boundary. Then, of course, if I have solutions on the boundary which shouldn't be there generically, well, how do you count? Well, you can push them into the space, out to the space, and then you ask what you can still count, yeah? That's the issue here. If you have problems with boundaries, but you can in some sense explain the boundary, and you want to say what I can count even if the things are very non-generic. So now we look. So we look at, we fix a commutative ring. Actually, it turns out you can fix a graded differential algebra here as well. So there are some, you can add more structure to the picture. So you're looking, so the first thing is, having this structure, you can define a convolution product. So it's, for many things, actually, it doesn't even have to be commutative. So you define the star product of 2 functions on this, on a letter C, by just taking all those partitions here which end at C. So since there are only finitely many degeneration sequences, the finite sum is well defined, and this axiom here below actually gives associativity. So now the counting of solutions leads usually, at least in this simple picture, you can make it more complicated if you want, to an element in C1. So you count, for example, this could be Z, the integers, and H of A is the number of solutions in this component A counted with multiplicity. Yeah, you could think of this. And then, now, remember, the boundary is explained in this way. So it turns out, if you look at a one-dimensional solution space, generically it would run to the boundary and decompose into things, which actually gives you this equation here. H star composed with H star is 0. Okay. So such a thing, such a count where this element lies in C1, let's call this a Hamiltonian. So now, because of this property, you can define a differential in this way by this commutator here, and dH squared is 0, which is a consequence of this. So now, so that's the general picture. Then you can talk about homotopy. What happens if you have homotopies? It turns out, if you give the right notion of homotopy, it is actually gives you certain homotopies here in some way. And that's actually quite interesting because it's extremely difficult to write down homotopies because they're so complicated. And you have, but you can formally write down some differential equations, and for small perturbations you get certain flows for formal differential equations, but you can make this rigorous. So let me talk about this. So if you have a ring, let me call lambda is this commutative ring. Let me say a piecewise constant continues from the left map, which only jumps at interior points. Yeah, so it starts, then up to some point it's constant, then it jumps, and so on. Let me call this a lambda map. Then a lambda measure is a map into this ring which only is non-zero at a finite number of interior points. So obviously, if I define the derivative like this, the limit, so here it continues from the left. If I take the value from the right, minus g, you can interpret this as a derivative. And then if you take the derivative, you actually get of a lambda function, you get a lambda measure. And if you have a lambda measure, you can integrate it like this. if you have an initial data. So now you can look at linear differential equations, and they are generated by the following. You look at families of maps into C0, so that for fixed letter, this is a lambda measure for all A. And you can look at this thing here. Now this here is a commutator, and it's a supercommutator. That means you take signs into account. So now you can look at this differential equation here, and you can show that under this definition, this thing has a unique solution given an initial data. So you have a Cauchy problem for this. And homotopies will come from these equations, in particular for small perturbations. So if you have a small perturbation, obviously you get a flow. So you get actually an isomorphism on the chain level for small perturbations for the theory. So now the interesting thing now is, in fact, for SFT is that you don't look for invariance in this whole ring, which I wrote down, but in subrings. And that's actually very important. So you have to look for additional symmetries. And of course, then if you have a subring which should be preserved, you get a condition a priori where your homotopy should lie, and then you can actually study algebraically what the conditions on the homotopy would be, and then you can go back to the problem and can study if you can actually realize this on the Fredholm level. So it gets an extremely clear picture. So you look at this general thing, you do a lot of algebra, and you can use cancellations and this kind of things to find additional ways of doing things. And actually homology is coming from this thing by using certain subrings. The representations of this lead to different theories. So let me say now here what is important. So what happens in application is the following. So we have these letters here, S, and then we have these relations. Now, in applications, quite often, certain letters are related. That means if you know the count for one letter, the solution count, you know it for some other letters as well. Just for intrinsic reasons of the problem, like here. In SFT, you take this curve here, which has 2 outgoing orbits, 3 ingoing orbits, and you add trivial cylinders to it. But the output and input is ordered, so there's some order. Then, in fact, if you know the count of this, you know the count of this up to sign. How you should count this thing. So that means a lot of the letters are actually related, and that means you can look for subrings which actually encode this relationship. So in practice, in order to describe this actually in a crisp way, when the symbols are related, then actually S should be a groupoid. So that means any 2 of these letters, there might be morphisms between them, but only finitely many, and so on. And the space of functions, which I used before, so the space of functions into this ring should actually be functors, where the ring is viewed as a category where besides the identity morphisms, you have multiplication by -1 from the object n to the object -n. And the maps, the rings are functors preserving this. And this you have to do actually in SFT to encode this thing. And then, of course, you want to have this subring and you want to have it preserved under the flow. So you have to study what does it actually mean for the homotopy algebraically, and then you look, can I actually achieve this analytically? So that gives an extremely crisp picture, and it's extremely hard to make mistakes if you never say it's obvious or leave it to the reader. Which was much easier with the other method, because it was so complex that you could easily do this. Here, everything is so split into really small steps. So that is the important question. So we have a subring of this large ring of functions, and then we want to look at infinitesimal homotopies, which actually preserve the differential. So what does it actually mean? So you can analyze what a differential equation, this concept actually is. So what it means is it preserves D precisely if the commutator of Ft with A lies in D for all A, there and for all times, and if this product here is 0 for all T. So it gives an algebraic condition for a set. If you look at a family of functions Ft in order to construct a homotopy, an infinitesimal homotopy whose integration would actually give you a chain map, which preserves also the ring structure, then these things have to be 0. So this comes here. That's actually, you have to be a little bit careful. So here, if you takes a product. So suppose you have two solutions for the initial value problem, and you take the product, the star product, and differentiate. You would say product rule holds. If the product rule holds, this term wouldn't be there. So you have to be careful sometimes. In this theory, because the derivatives are Dirac functions, the product rule does not hold. So you have this rest term here, and you see, if these are solutions and you only have this part of the differential equation, it preserves the product. So you want to have this 0 here. So, and we're coming to an end, almost. So now here, that's sort of the algebraic theory. If you want to find interesting invariants. So the picture is now here. What I do at the beginning is just I'm encoding in a very broad, flat way all the degenerations which I have. And then I can look at symmetries in this picture. And then I can bundle the data in different ways. And that would, for example, lead to what we did in SFT. But that's not the only way. So I could, for example, view in this theory related symbols as unrelated, gives me more freedom in the perturbations, and I get a different homology group, for example. Might not be useful, but there are a lot of possibilities. So you are given a subring of the space of all functions, which encodes certain symmetries, and then you consider at all functions f on the graded 0 level, which have this property here. And an infinitesimal homotopy must take values in this thing in order that the flow associated to this maps D into D and preserves the star product. And you can study this. Then, of course, then you have to study the Fredholm problem and have to say, so how do these functions ft arise? They arise from studying one-dimensional families of Fredholm index -1 problems. This is what the homotopies come from. You look at Fredholm index -1 problems, but in one-dimensional families. Now, if the letters are unrelated, you can make the times different generically when they actually have solutions. If you have two Fredholm problems in two unrelated Fredholm problems in two families, they will not have at the same time a solution. However, if the Fredholm operators are related on related symbols or related components, obviously that's impossible. So in this case, there must be a fantastic cancellation in some way or the other. Or you have to write down homotopies in such a way that the cancellation occurs automatically. But you can study this in the terms of the algebra. So that is sort of the picture. And in fact, that I already pointed out, and then I'm done, it is very good to actually go to this algebraic picture here, calculate these things here, you can calculate the applications, and then you know what algebraically has to be true. Then you look here and you want to have a perturbation of this in this way. Of course, as I said, the big space is an orbifold type space, a retraction divided by a finite group. So now, if you want to keep that symmetry in general, you can't make this transversal, but of course you can use multi-valued perturbation if you want to overcome this problem. So like, if you have a symmetry to preserve, you just take enough perturbations, that's a set of perturbations, has a symmetry, then you calculate the invariant for each of them, you just integrate and average. That's the way to do it. I mean, it's at least a simple-minded way. So you have to take multi-valued perturbations, but then you have this additional other structural requirements, which are much more important. And you can analyze this, and you see what kind of families you can actually take of multi-valued perturbations, and then in SFT you can show that certain subrings can be preserved, and then you represent them, and you come to the formulas which were written down. So that's the general picture. Okay, and maybe you get an idea why it takes so long, but there's a lot of things which you had to resolve in order to get to this picture here. Okay, thank you.